This is a presentation about the challenges and solutions for characterizing 112 gig PAM4 electrical signaling. It's being presented by MultiLane on behalf of the TestConX 2020 conference. Today's presentation will cover the following topics: product test cycle, advances in AT testing, PAM4 signaling, 112 gigabit Ethernet challenges and solutions, multi-purpose AT testing, and then we'll end with examples and a conclusion. High-speed serial products will continue to rise in demand as hardware virtualization, 5G, and artificial intelligence revolutions take off. In all cases, moving lots of data between vast networks of computing engines is demanding higher bandwidth pipes to keep up with the computations. In order to ensure the best quality and reliability at an affordable cost, the 112 gig devices are tested at each stage of product development. It becomes increasingly costly to find failing units as you move from wafer test to package test to product to system level test. Screening at each step allows the engineering team to better characterize and improve each step. It also allows them to reduce overall cost by eliminating failing devices as quickly as possible. Here we're showing a new automated test equipment strategy for 112 gig test and measurement hardware. Prior to 2019, MultiLane worked with its customers to include MultiLane instruments directly onto the DUT load board. This allows the MultiLane instruments and cabling to be as close to the DUT as possible and to more easily prevent cabling from the instruments to the DUT without interfering with the handler to test head docking mechanisms. In 2019, MultiLane and Advantest partnered to create a more modular approach that can be used by all Advantest 93K users to test 112 gig PAM4 devices at both wafer and package high volume production test. By redesigning the MultiLane instruments and housing them into an extension box sandwiched between the test head and the prober or handler, all Advantest 93K users can now use the same MultiLane instruments in different configurations inside the extension box, eliminating the need to replicate the high-speed I/O hardware on every DUT load board. In addition, the instrument's software is integrated into the Advantest SmartTest GUI software tool suite, reducing instrument setup and measurement times by as much as 10x. In summary, this new hardware-software strategy allows reusable and modular PAM4 test and measurement instruments inside the test head, faster test program development cycles, and faster test times. Here are some examples of PAM4 hardware. The left side of the slide shows the testing challenges of transmitting PAM4 signaling to the DUT. Transmission is accomplished by using a programmable pattern generator with different functionality, including various industry standard PRBS patterns, transmit equalization to de-emphasize the signal pathway to the DUT and to also allow intentional signal corruption to stress and characterize the DUT receiver for real-world conditions. The pattern should also be able to intentionally insert bit errors, perform gray coding, polarity inversion, and sine wave generation. These transmit features are found on MultiLane BERT instruments, which also provide various tools to analyze the DUT's bit error rate coming out of the DUT transmitter. FFE and DFE functionality to reduce the effects of inter-symbol interference. Also, bit error rate counters with and without bit error correction. On the right side are the kinds of features required by the high-speed I/O oscilloscope. Of course, fast acquisition is important to reduce test times. Wide acquisition dynamic range is also important, as high-speed signals transmitted from the DUT will have varying levels of signal loss due to different cabling and connector challenges. The scope should contribute very little jitter to the sampling measurement and be able to decompose the received signal into its total jitter, random jitter, and deterministic jitter components. The scope should allow persistent eye diagram views and be able to analyze the various eye mask measurements for individual eyes as well as comparative data between the three PAM4 eyes. The scope should have both analog and digital equalization tools to bring the DUT transmitter output into focus, much like a pair of glasses help you put the words on a page back into focus. The equalization tools should include analog techniques such as CTLE and DFE, and also include digital techniques such as S2P, De-embedding software. And finally, the scope should have an adequately fast sampling rate and input bandwidth, such as MultiLane's scopes having 100 megahertz sampling rate and a 50 gigahertz input bandwidth. So why use PAM4 signaling? Why not just double the speed of NRZ binary signals? The problem is that we're reaching switching speeds that are approaching unacceptable signal losses. PAM4 was introduced to allow the same transition frequency to provide 2x the bit information by using 4 signal levels instead of 2 levels in the voltage domain. Using PAM4 allows the transmission frequency to remain the same while doubling the bit information. Here we see an example showing how lossy a transmission channel can be at 13 gigahertz. A 13 gigahertz Nyquist switching frequency allows 26 gigabaud or 26 gigasamples per second for both NRZ and PAM4. However, for NRZ, this translates to 26 gigabits per second, while for PAM4, it translates to twice that, or 52 gigabits per second. Same switching frequency, but 2x the bit information for PAM4 versus PAM2 and NRZ. While PAM4 allows 2x more bits at the same Nyquist rate, it poses additional transmitter and receiver complexity in the voltage domain. Instrumentation must be able to sample and analyze these more complicated PAM4 signals that are now both high speed as well as 4 signal levels instead of 2 signal levels. The most prevalent example of PAM4 sampling are its characteristic 3-eye diagrams shown to the right of this slide. The 4 levels in the eye diagram each translate to 2 bits of symbol information shown as 1, 1, 1, 0, 0, 1, and 0, 0. The eye diagram parametrics for NRZ's single eye diagram have been extended to also include statistics that provide comparative information amongst the 3 different eyes. TDECQ is the new transmitter figure of merit. It's a mask margin test for PAM4, and it predicts system-level performance. It's the ratio of how much noise can be added to the transmitter signal versus an ideal signal and still maintain a targeted symbol error ratio. It mimics the behavior of a real receiver after equalization has been performed on the received signal. Of course, AT instruments should be able to perform at-speed TDECQ measurements. Other measurements, such as eye width, eye height, linearity, and skew, should also be available from the AT instrumentation. Another challenge for the test environment is removing or de-embedding the signal losses inherent in the cabling and connectors between the PAM4 instruments and the DUT. In a real-world situation, these effects will also occur, so that the DUT must have enough transmit and receiver margin to still maintain an acceptable signal error rate in the real world. When the instrument is sending a signal to the device receive input, it must de-embed the effects of the tester cabling connectors. However, at the same time, it must also be able to distort the de-embedded signal to properly margin the DUT receiver input. In other words, the instrument should be able to provide a perfect signal to the DUT receiver as well as an intentionally corrupted signal similar to real-world conditions to the DUT receiver input. In the opposite direction, the path from the DUT transmitter to the measuring instrument also experiences signal losses through the cabling connectors. These signal losses must also be de-embedded by the measurement device so that all measurements are mapped back to the DUT transmitter output without any signal degradation introduced by the test setup. Various methods can be employed to correct for channel losses. In method 1, a frequency domain method can be used. By injecting sine waves at various frequencies through the DUT setup, a frequency versus amplitude plot can be generated. This plot will show how signal loss increases with frequency. By creating an inverse model of this frequency plot and convolving its time domain representation with the sampled signal, the frequency response of the test setup can be computationally flattened in the frequency domain. Method 2 shows how intersymbol interference can be compensated for in the pattern generator. By feeding an initial signal from the pattern generator through the test setup and then to the scope, intersymbol interference can be measured and FFT taps can be calculated. These FFT taps are then used by the pattern generator to pre-distort the transmitted signal to reduce the intersymbol interference symbol effects. Method 3 shows the error detector of the BERT using a combination of analog circuits, such as continuous time linear equalization, or CTLE, as well as FFE and DFE taps to compensate for intersymbol interference effects. In all three methods, the main takeaway is that the channel losses and ISI can be calibrated out of the DUT path through sophisticated methods employed by the BERT and the DSO test equipment. These methods become increasingly important at 112 gigabit Ethernet PAM4 speeds because all of the signal losses mentioned here become much worse as the Nyquist frequency increases and as we move from 2-level to 4-level signaling techniques. Here are some examples of DSO embedding using multi-lane instruments. In the top right, the DUT puts out a PAM4 signal with an eye diagram having a noticeably good eye opening. Unfortunately, once this eye diagram reaches the DSO, it is distorted due to high-frequency channel losses. The multi-lane DSO successfully de-embeds its DUT signal and recreates the original DUT eye diagram for pass-fail processing. The PPG, or pulse pattern generator, should be able to add signal preemphasis to accommodate for signal losses from the PPG to the DUT. The digital scope can sample the PPG signal at the DUT location. FFE taps in the PPG are programmed, and then the desired signal can be realized at the DUT receiver. The lower left picture is the PPG signal at the DUT before being calibrated, before preemphasis is added. The middle picture shows the scope's desired signal at the DUT. The right picture shows the PPG signal at the DUT after the FFE taps are loaded. Another important task is calibrating the BERT and the DSO instruments inside the test head. Here's a representation of MultiLane's calibration kit. The benchtop 4035 is a scope and BERT in one unit. It is used to calibrate the cassette, BERT, and DSO instruments. Customized cables directly connect the benchtop instrument to the cassettes. Along with simple-to-use automatic software, calibration can be performed. Another area of testing that hasn't yet been addressed is the DUT load board. So far, we have talked about the BERT and DSO instruments that are separated from the DUT load board. However, additional data cards can be used to allow additional flexibility by allowing a simple reconfigurable load board design. This has the following benefits: simplified, reconfigurable load board design, a solution to test high port count devices, the ability to use the same load board for characterization, high volume manufacturing, thermal, and system level testing applications, modular personality cards for different applications, flexibility to test a DUT on the same platform for both R&D and high volume manufacturing, access to external and internal instrumentation, and access for probing, control, and power. Daughter cards can be configured on the DUT load board in such a way that high lane counts can be tested on the same test head with multiple insertions. Up to 8 daughter cards can symmetrically surround the DUT socket. The same AT load board can be replicated with different daughter card configurations. For example, one daughter card type might steer some gigabit Ethernet channels to DC parametric resources, while a different daughter card steers other channels into loopback mode with a predetermined level of signal attenuation. Using 2 DUT insertions, 2 identical load boards with different daughter card stuffings accomplish complete DC and AC parametric testing on all channels. Here are some examples where the daughter cards have been placed down onto the load board in 2 different configurations. On the left side, we see the NS6040 handler's docking plate located in the middle of the load board, and the daughter cards surrounding the docking plate. The docking plate being the white rectangular assembly in the center of the load board. On the right side, it's a more circular pattern because without the docking plate, the daughter cards can be placed closer to the device under test. A variety of daughter cards can be imagined with different end results in mind. Here we show some examples, including an optics daughter card to test how the DUT electrical signals work with the attended optical hardware, 18 dB attenuation daughter cards for loopback testing, splitters and breakout cards to allow external instrumentation access to DUT signals, golden devices, and even daughter cards to help with PCIe Gen 5 testing. Personality cards can expand the versatility of DUT load boards by allowing the integration of the tester resources, external test and measurement, and system-level products to all simultaneously interact with the same device under test. This daughter card allows a connection between the DUT and external optical cables. In this way, the DUT can be verified to work in a system-emulated environment while still being connected to the tester resources. Other daughter cards provide varying amounts of signal attenuation into the loopback path and controlled noise injection into the signal path. Resistive splitter daughter cards allow a device under test transmit signal to be simultaneously looped back to its receive input while simultaneously steering the same transmit signal to signal integrity instrumentation. Daughter cards can also be used to hook up different test equipment using 60 GHz RF switches, 40 GHz splitters, and 40 GHz wideband bias Ts. RF switches for when instruments will be connected or disconnected, splitters that can allow multiple pathways at the same time, and bias Ts are often used to provide a DC path for DC parametric testing with minimal disruption to the signals going through the high-speed AC path. Let's look at 2 examples. In example number 1, a transimpedance amplifier is to be characterized. The BERT's programmable pattern generator, generates varying sine waves, and the DSO samples the output of the TIA driver to understand the TIA's frequency response. In the second example, a TIA with integrated clock data recovery circuit presents both the TIA outputs along with the recovered clock to the BERT. From this, a bit error rate can be calculated. Here are the outputs from a real TIA plus CDR example. This is a subset of measurements, but they lend themselves well to a visual. In the left picture, we see bit error rate versus acquisition samples for different input power. In the middle picture, we see PAM4 4-level eye diagram from which the DSP software will calculate the various statistical information for the test engineer. And in the rightmost picture, we see gain versus frequency plots for different amounts of power bandwidth. In conclusion, 112 gig/56 gigabaud PAM4 is the new electrical optical high-speed Ethernet standard. Testing is required from wafer level through system test. 112 gig BERTs and DSO solutions are available in ATE format. Signal integrity measurements require special attention. Multi-purpose ATE test solutions are required to enable the full product test cycle. We thank you for spending the time to listen to this presentation. MultiLane is available to answer follow-up questions that you might have.